Hello everyone, welcome to my first video, where I will talk about the how and the why the Fundamental Theorem of Calculus works. So, you might have already known that the integral of a to b, where of course we assume that a is less than or equal to b, of f of x, of some function, dx, yields the area under the curve, where as a picture as an example, where this is f and this is x, right, and this might be the func curve of f of x, right, then if this is x equals a and this is x equals b, then of course this integral will give the area of that much. And you might wonder, like, is there a relationship between the derivative and the integral? I mean, it might be not, I mean, it may not, you may think intuitively, probably not, because, well, slopes and areas aren't really the same, don't really even look that similar in the first place. But nevertheless, though, the Fundamental Theorem of Calculus tells us that there is indeed a very significant relationship between the two. And we can figure out that, and we can see that by the Fundamental Theorem of Calculus. So here's the first part, because there's two parts to this theorem. And the first part is if f is continuous, then we know that, then we can say that if there exists a function capital F of x such that it is equal to the integral of some constant a to x of f of t dt, and I chose that t to be an arbitrary dummy variable, then it is known that the derivative of f, or the derivative of the integral from a to x of f, is simply f of x itself. And this is very significant, because what this tells us is that the derivative operation and the integral are actually inverse operations of each other, which is kind of cool, right? Because you don't really think that derivatives and areas kind of invert each other in any sense, but it actually is, in fact, shown by the Fundamental Theorem of Calculus. So first, let me show you a proof for why this is the case. And I will try to not go too technical, right? Just to make it easy for everyone to understand. So let's start with the fact that we declare f of x is equal to a to x, or the integral of a to x of f of t dt. So basically what this capital F function does is that it receives an input x, and the output will be the area under the curve. So basically, if I were to show you a diagram, if this is a and that is x, where we can change this input of x, then this area will be capital F of x. So basically, if you input a second limit of integration, then the function capital F would yield the area. And of course, our question is, well, how are we going to, take the derivative of something like this? Well, luckily, we know how to take the derivative. And that is because we can think that the only way that we can think about taking the derivative of something like this would just have to be using the definition of a derivative. As a small recall, remember that if you want to find a derivative of any function, say g of x, maybe, then the derivative of g at x is equal to the limit as k, I'll just call k approaches 0, of g of x plus k minus g of x divided by k. Basically what this says is that we're just taking the limit of the slope between 2 points and just divide by the change in x, right? So basically, we're doing it by the change in the output of g between the 2 points, of x and x plus k, divide by the change in x, which is k, because x plus k minus x is k. And so we will use the same thing here. So first, we want to find what capital F prime of x is, which is basically this thing here. And this is equal to the limit as k approaches 0 of f of x plus k minus capital F of x all over k. And plugging in, and I want you to notice that basically for any x value here, that x value has to be the same as there. So this means that this is equal to the limit as k approaches 0 of the integral from a, and this x value is x plus k of f of t dt. And we subtract that by capital F of x, which is just a to x because that x is up there, and f of t dt, all divided by k. Now you might wonder, how are we going to compute the difference between two integrals? Well, luckily though, there is a geometric property of integrals that we can use provided that f is continuous. And that is, suppose we had a graph like this. And this is f of x. And let's just say that we just chose this to be a, this to be x, and this to be x plus k. Notice that the integral from a to x plus k is this amount, right? We go from this x value to that x value, and that area of all of that yields the integral. And let me erase that. And then, but then on the other hand, the integral of the after the minus is a to x, which means that we need to compute the integral of this amount, which is that amount there. And so notice that because we're subtracting the area between here and there, what we get is just the difference of this amount. So hence, the numerator's difference would simply just be the integral from here to here. So integral from x to x plus k of f of t dt. Okay, and so rewriting what we had up there, this is just simply equal to the limit as k approaches 0 of the integral from x to x plus k f of t dt, all divided by k. And now you might wonder how we're going to compute this, right? Because after all, that just yields an area, but then you have to divide it by k, which is approaching 0. And so again, we're going to use our geometric understanding of area. So let's just suppose that we have this. So this is f of x again, like that, and this is x, and this is f of x. And now just imagine that you're here, where this is x, and this is x plus k. And I want you to note that delta x here is just k. And so, and also we also note that this is f of x, and this is f of x plus k. And so one thing that we have to think about is, well, what happens if k approaches 0, i.e. what happens if we shrink the width of the rectangle? Well, the more we shrink the width of the rectangle, I want you to notice that the more you shrink, the y values between here and here become sort of approximately the same. And this makes sense because it's kind of intuitively, if you kind of let k approach 0, then this k value will get closer and closer to 0, and if it gets closer and closer to 0, then you can see that it becomes the same thing as f of x. So we use this idea that because the two y values are about the same, they're almost a rectangle. So basically, x to x plus k of f of t dt, well, using the geometric property that the integral represents the area under the curve, this thing is just nothing more but just k, right, because this is delta x times f of x, where this represents the height. And of course, you know that the width of a rectangle times the height will just yield the area of that rectangle. So rewriting what we had up earlier, this is just the limit as k approaches 0. And of course, remember that we're computing the derivative of capital F with respect to x. And of course, this is just k times f of x over k. And of course, you can see that the k's cancel out before we take the limit operator. And hence, this equals f of x. And of course, I showed you that the derivative of capital F is equal to f of x, which is to say that the derivative of the integral from a to x of f of t dt is equal to f of x, which shows that the derivative of the integral of f yields the function back itself. And that's it. Of course, this was sort of geometric, but I do think that using graphs really helps us understanding how derivatives and integrals are related. And so next we move on to the second part of the theorem. And that is, let's just say that f of x was continuous, right? I mean, I think that's a pretty obvious condition for the interval of a to b, i.e. a is less than x is less than b, and within this interval, we assume that f is continuous. Then, if there's a function capital F of x, such that the derivative yields f, hint, hint, you may want to use the previous one where f of x is equal to a to x is f of t dt, right? Because we know that the derivative of this yields f of x, which satisfies the property that I just mentioned a few seconds ago. And we know that if this is true, that there exists a capital F for every normal f of x, then it turns out that the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. And as long as you know the antiderivative, so this function is called an antiderivative, then we can easily compute any integral that we know. And that is why there's often, if you search up on the internet, there's often tables of antiderivatives, but it's really kind of like saying like, oh, what function, if you take its derivatives, yields back our original function that we had in the first place, f of x. Okay. All right, so now let me show you the proof of why this is the case. And luckily this one is not so long since we already done the first part, which kind of helps. So first, let's start off with the fact that f of x is equal to the integral from k to x of f of t dt. And I will let the fact that k is between a and b. And you will see why this is helpful later, because the reason why this helps is that we only know that f is continuous from a to b. So if we choose a middle value, then we know for certain that x equals k, f is still continuous by our conditions that we earlier imposed. And so we can, first I guess we can start with the fact that if you had a picture like this, and we had a, k, and b as I showed you earlier, right? Then you can see that the integral from a to b is simply equal to the integral from a to k of f of t dt plus the integral from k to b of f of t dt. But remember that I defined in the beginning that capital F of x is equal to the integral from k to x f of t dt. And you can see that there is a significant relationship between for this and this, because you can see that for this one, the x up here corresponds to b, and this one, it's similar, but it's just that the order is flipped. So we'll deal with that in a minute. But first, let's simplify this one, because we know that by definition, since x is equal to b for this integral, it is equal to capital F of b. So therefore, we set this equal to the integral from a to k of f of t dt plus capital F at b. Now, there's another property, because since we know that a is less than k, but we want ideally our k to be on the bottom, so we want to flip it. And there is a property in integrals, or a geometric property, that whenever you want to flip the order of your limits of integration, then you do the minus of k to a. So notice I flipped it, but there's a minus sign in front in exchange for that, of f of t dt plus f of b. And we can see that our x is now a, so this essentially is minus f of a plus f of b. And remember that from the beginning we were saying this equal to a to b of f of x dx. And so hence, this is the same thing as saying that the integral from a to b of f of x dx is equal to capital F at b minus capital F at a. And of course, this is the thing I wanted to prove to you in the beginning. All right, and that's it. And that ends my theorem and proof for both parts. So now I would like to summarize what we've just been learning from the start. So I just want you to remember that if I scroll back up, that we were curious about what's the relationship between derivatives and integrals. And I just showed you here that if f of x is a continuous function, then the derivative of the antiderivative. So recall that this is called an antiderivative because the derivative of f gives us back f. And so the derivative of the antiderivative of f yields back the function f itself. And of course, I showed you the geometric steps that led us to this conclusion. And then the second part of our investigation was, well, how do you compute? Well, if you know that the derivative of the antiderivative of f is just the original function f itself, then we were curious about, well, what happens if you want to find the integral between a to b? And we found out that it was simply just the difference between the antiderivative of f at b and the antiderivative of f of a, which we just simply used a few geometric properties, and that led us to our conclusion. All right, and this ends my video, and I thank you for your attention and for your interest, and I hope that you will find my future videos more interesting as I will delve into more multivariable calculus in the future and such. Thank you very much, and please subscribe, and have a nice day, everyone.